I think research is just the pure joy of discovery. It is when something doesn't behave the way you expect it to. And then all of a sudden you say, hey, I didn't know that, but I can use that for interesting things.
The commitment that the university has made to quantum information science is really exciting. It involves people from material science, electrical engineering, optical science, physics, mathematics. Everybody on campus is involved.
And what's important is we're actually translating that excitement into investments, especially in the area of quantum optical networking.
My team is working on building the foundations of what could become the quantum internet of the future. We are building various technologies, subsystems that will go into building a quantum network that can connect many quantum processors that are separated by long distances to bring out the power of quantum information processing in a much more profound way than is possible with a single quantum processor.
We come from different backgrounds. For example, we have quantum information, we have material sciences, and we have nanophotonics, and we have free space quantum optics. But we have a convergent effort to realize this very challenging goal. That excites me a lot.
We are also working on using entangled cluster states of light to build quantum repeaters. Quantum repeaters are a special purpose quantum processor that will go into the node of a quantum network, which will enable quantum communications at a much faster rate over much larger reach than is possible with direct communications.
The technology we are going to use is nanofabrication technology. It's the centerpiece. It's a very similar technology you use to fabricate your computer CPU in your phone or your laptop. And so we fabricate a lot of nanophotonic devices on a single chip. And we create controlled quantum states on chip, and then we detect the quantum state on chip. That's what we do every day.
Once we have all the quantum technology that gets to the scale that we are envisioning right now, there will be a whole lot of applications beyond what we can even currently imagine that will revolutionize how we process, communicate, and sense the world.
The things we're investing in is building up what we call a quantum testbed. So this is something that across campus, it'll interconnect different departments, different buildings with what we call hot and cold running entangled photons.
We are going to have a central facility located in the basement of electrical and engineering building, and we're going to build entangled photon sources, and we're going to pull optical fibers to distribute these entangled photons entangled with each other to different labs.
So you can do application development. And that could be anything from biological imaging to communication technology. It's a pretty unique facility that we're going to put together here.
Just like the inventors of the ARPANET could not imagine all the computing and communications power that we all hold in our pockets today, there will be a slew of new applications that just go far beyond our current imagination.
One of the exciting things about this kind of research occurring at a university is the opportunities for students, for undergraduates, graduate students, PhDs, and postdocs. This is the cutting edge, this is the future, and it's great to be at the University of Arizona where we're leading in the development of this technology.
It's a relatively young field, so which means there would be a lot of opportunities and unknowns to explore.
One of the things that's exciting about the current moment is that now we can kind of see that we can take quantum mechanics teaching, and also quantum optics teaching for that matter, in new directions. We can take a different tack. We can say, hey, you can think of quantum mechanics as about how you can encode information in a physical system, how you can process it using a Schrödinger equation, how you can read it out according to the rules of quantum mechanics. And once you can do that, you can do some fundamentally new things.
I think the best part is that you are basically touching the boundary of the current technology. So you are doing things that no one else can do, but you have to do it because people see that we have to have this technology in the future.